What if there were a rule that told you which dreams of perpetual motion will never work? What if there is a limit that tells you how efficient your engine can be at best, why ice melts, and even how living cells power themselves? That rule exists. It is the second law of thermodynamics. According to first law of thermodynamics, energy is conserved, but according to second law of thermodynamics, the quality of energy degrades when it spreads out. Heat tends to flow spontaneously from hotter to colder bodies, not the other way around. Due to this, no cyclic device can take heat from a single reservoir and convert it entirely into useful work. The second law is the most honest constraint in science because it tells you what cannot be done, not just what one desires. The story begins with steam engines. In 1824, Sadi Carnot asked a radical question: what is the maximum possible efficiency of any heat engine, regardless of its design? His thought experiment created the Carnot cycle and showed that the upper bound depends only on temperatures, not on the working fluid. In the 1850s, Rudolf Clausius and William Thomson, Lord Kelvin, sharpened the law and introduced entropy. By the 1870s, Ludwig Boltzmann connected entropy to probability, revealing a statistical arrow of time. Carnot imagined an idealized reversible engine operating between a hot reservoir at temperature Th and a cold reservoir at Tc. The working substance goes through 4 reversible steps and returns to its initial state. The only way to get net work is to absorb heat at high temperature and reject heat at low temperature. Path 1. Adiabatic compression, compression. Path 2. Isothermal expansion while maintaining high temperature. The system draws heat from the hot reservoir and expands slowly, doing work while its temperature stays constant. Path 3. Adiabatic expansion. The system continues to expand without heat exchange, so it cools from high temperature to cold temperature while doing work. Path 4. Isothermal compression while maintaining cold temperature constant. The system compress and heat is rejected to the cold reservoir at constant temperature. The power of Carnot's logic is that it ignores engineering details and still sets the ultimate ceiling. Practical engines mimic Carnot's idea with approximations and accept irreversibilities. The Otto and diesel cycles drive automobiles with rapid combustion and finite-time processes. The Brayton cycle powers jet engines and gas turbines. The Rankine cycle runs steam power plants. All of them lose efficiency to friction, turbulence, finite temperature differences in heat exchangers, and non-ideal fluid behavior. As a rule of thumb, modern spark-ignition car engines achieve on-road thermal efficiencies around the 25–35% range. Advanced diesel engines can exceed 40%, and state-of-the-art combined cycle power plants can surpass 60% by stacking Brayton and Rankine cycles. The second law does not just cap efficiency, it explains why every percentage point is hard-won. Clausius summarized the second law for cycles in an inequality. For any cyclic process, the integral of heat over temperature is never positive, and equals 0 only for a fully reversible cycle. Boltzmann connected entropy to microstates. The arrow of time emerges, because overwhelmingly more microstates correspond to mixed or spread out energy than to ordered ones. Biology. Cells are non-equilibrium machines. They export entropy to maintain local order. ATP synthase uses a proton motive force across membranes to synthesize ATP, functioning like a nanoscale rotary heat engine driven by chemical and electrostatic gradients. Diffusion, osmosis, and active transport all reflect second law constraints and costs. Climate and geophysics. The atmosphere acts like a heat engine driven by solar heating differences. Hadley cells and mid-latitude storms move heat poleward, producing work that appears as winds and waves. The second law explains limits on idealized hurricane intensity and the need for temperature contrasts to sustain circulation. The second law is not just about heat, it is about possibilities and limits. Carnot's cycle sets the ceiling for engines. Real machines chase that ceiling and pay an entropy tax along the way. From cells to storms to computers, progress comes from smart entropy bookkeeping. My opinionated summary: if you want to innovate in energy, biology, or computing, learn to think in temperature gaps, free energies, and irreversibilities. The second law will not yield, but it will guide you.